Good day, everyone. Welcome back to another quiz section of this lovely tutorial class. Today we are going to be looking at a very important topic, which is moment of a force. Moment of a force. Now, before I go into this topic, I'm just going to introduce the topic to you guys. You guys know the meaning of movement. When I say moment of a force, what do you actually mean? That's what I'll be doing here. But now, if I go to this topic, ensure you do these things. Ensure you like this video, share it to others. Don't skip any part of this video. Very, very, very important. Now, moment is the product of force and distance. Just as work is also the product of force and distance. That's what we're going to ask. Moment and force, are they not the same thing? No. Work is the product of force and distance moved in the direction of that force. That is work. Work done is the product of force and distance moved in the direction of that what? Of that force. But moment is the product of force and a distance that is perpendicular to the point you are taking the moment from. So that's why if I ask you what is the moment about this of this force, I will not ask you what is the moment of this particular force, because if there is no force, there will not be moment, because moment must be the product of force and perpendicular distance. That is the fundamental definition of moment. Now, if you now take this moment about any point, the thing will tend to something like there are some moments that will tend to twist around that point. We call them twisty moments. There are some moments that will tend to bend maybe the material about that point. We call it bending moments. So if I have this point as point A now, I have this point at point B, and I ask, what is the moment of this force about this point A? What you just do? Multiply this force and the distance between this force and point A that is perpendicular to that point A. So moment is actually force times perpendicular distance. Now when you know perpendicular distance, the distance that makes an angle of 90 to the point in question. That is not perpendicular distance. Is that what? That makes an angle of what? 90 to the what? To the point what? In question. So what is the next thing now to do? What is the next thing? The moment about A now from definition will be force. Look at it. So this distance makes an angle of 90 to this force. So from here to here now is a perpendicular distance. So from here to here is a perpendicular distance of A to this force F. So that will be F times what? Times D. That's the moment about point E. Now there are some rules to use the moment. There are some rules to use what? We use the moment. Now we have sagging moment, we have hugging moments. Now I'm not going to that because that belongs to structural analysis. Now the next one I'm going to look at is some rules in moment also works with the rules we have in statics, because moment is actually a topic in statics. Remember, statics is the what? Study of effect, or is a branch of mechanics that deal with study of effect of forces on bodies at rest. We have structural statics or structural analysis. We have structural mechanics or solid mechanics. We have fluid mechanics as well as fluid statics and fluid dynamics. That is why in this topic or in this part of mechanics, we'll still be looking at dynamics. Dynamics is the study of bodies in motion. That can be studying a body in motion in the sense that we'll not be looking at the forces causing that motion. We call that aspect kinematics. But when we're not considering the forces causing the motion, we not call the aspect of mechanics dynamics. Now, if you're not looking at forces on body that are not moving, forces on body at rest, we call it statics. Now, this body here, this member is not moving. The member is not what? It's not moving. So look at what we're going to do now. But I saw moment at this point. And this moment just say this is this. Now, one of these moments is that we have two types of moments. We have two kinds of moments here. We have one we call anti-clockwise moment. Anti-clockwise moment is a type of moment that will tend to rotate this member here, or let me call it a body, or what do we call it? We call call it beam in structure. So you can call it a rod. And because you are just coming up. But it's not we can call it this is called a cantilever beam. Fixed to one end and free at the other end. That's what we call it. So this is a cantilever beam in structures. So this beam can either bend towards this side or bend towards the other side. So movement that tends to bend it towards the other side is called anti-clockwise, or rotate it towards this side to this side. It's called anti-clockwise movement. The one that will rotate the beam in the clockwise direction is called clockwise moment. So the sum of one moment is that the sum of all the clockwise moments must be equal to the sum of all the anti-clockwise moments. That means the sum of all the moments of a force about any point that will rotate the beam to the clockwise direction must be equal to the sum of all the forces of the moment about a point from the forces present that will rotate the beam to the clockwise direction. So that's one thing you should know. Just take care of it. Just take care of that. The next, just very well now. The next thing I'm going to do now is to no, we are not looking about sign here. I'm not looking about sign here. And it's not that if you use sign convention, this force may be at the end of the day it will be negative. The force will be negative at the end of the day. But I'm not talking about sign convention anymore. We are just doing introduction to what is it called to moment. Most cantilever beam give negative moments. Okay, so let's say we have something like this. Let's have something like this. Another beam. Let me draw another beam here. Another beam of this nature. So we have a beam of this nature. In moments, just one moment, let's say the moment you do in secondary school, we call it meter rule. They will peg it here. I'll peg my own here. So this is what I'm doing now. Now these structures actually these structures. Structures are doing this way. For ordinary, this we don't put to say we have a pivot here, we have a pivot, we call it pivot or fulcrum. Or something like hinge is hinge at this point and this point. So let's assume the weight of the meter is actually at the center. The weight of the meter is at the center. Let's call it the weight. So another rule of movement is that all downward forces will be equal to the upward forces. So let's go to point A now. I call it point B. If I ask you what's the reaction at A, what's the reaction at B? What you just tell me, as far as going down, there will be a reaction means something that will something like trying to counter this movement. So that it will be coming here this way. So we also have horizontal reaction there as well. Because something, this is a pin. In major structure, something like this, we call it a pin. Something like this, we call it a pin. That's what we call it. This is the pin. Then something like this, we call it a roller. Something like this. Call it a roller. Call it a roller. This is the beam. This is the beam. There's something like this, we call it fist or built-in support. This is a roller support, built-in support, fist support. Then this is a pin support or hinge. So this one have one reaction in the vertical direction, so I have two reactions in the horizontal and vertical. So I have three reactions, horizontal and vertical, and a bending movement. Not that it is bending, this and this is bending. But this one cannot rotate, this and this can rotate. Well, let's do that. Let's just look at the one we are doing. But because there's no horizontal movement, we will not put this one here. The same thing, we have another reaction here. We have another reaction here. Another reaction here. So this will be the reaction at A, so that one will be the reaction at B. So another rule of movement is that the reaction, that is all upward forces. The upward force here is this one and this. That is the reaction at A and reaction at B. Must be equal to all downward forces. Downward force is the weight of the beam. This what? Just another rule use movement. All upward forces must go to what? The downward forces. Now, let me say, I want to give you a question. Now, let's say a meter rule is part of weight 50 grams. A meter rule of weight 50 grams is pivoted at both ends. Pivoted at both ends. Obtain the reaction at pivot A and pivot B. Obtain the reaction at pivot A and what pivot B. You see the meter is like this, and meter is like this. The meter is like this. meter rule. And it's pivoted at both ends. You have pivot here, you have pivot here. Then the weight is what? The weight will be at the center. If meter rule is a balanced meter rule, it will be at the center. It says 50 grams. So this reaction at A, this point B. Reaction at B will be like this, arrow A. Reaction at B will be arrow B. So if I ask you now, what's the reaction at A, what's the reaction at B? Just come and tell me that. The reaction at A plus reaction at B will equal to 50. Why? Because we were told that, remember it's in grams, so it's in grams. So we can do something like this and we convert this one to Newton. And we decide to convert to Newton. To convert something to Newtons, what we are going to do will be, before we convert something to kilogram, we multiply it by 10. Because our G is 10. Our G is 10. So 10 meters per second squared. So that's what we are going to do. That's what we are going to do. Because this weight is supposed to be in either newtons or kilonewtons or newton. Those will have the unit of force, not the unit of mass. So this one is grams now. So this one will be something like divided by 0.05 kilogram. Multiplied by 10 again will be 0.5 kilogram. So that multiplied by 10 will be 0.5 newtons. So I'm going to take it at 500 grams. So that's going to be a little bit big. 500 grams. So if you divide that, multiply 1 kilogram and divide by 1000, you have 0.5. Then multiply by 10 again now. Multiply by 10, you have 5 newtons. So you have 5 newtons here. So this will be 5 newtons. That is the weight. I hope you understand that. But if this G is related to gravity, just 500 multiply 10, that will be 5000 newtons. And that's some question will say is 5G newton. That G will now be associated with gravity. But I'm telling you it's 500 grams. Divide to newton. But divide by 1000 divide to kilogram. Then to 1 kilogram to newton multiply by 10. Because we said G associated with gravity is what? It's 10. The next question will be okay, let's say since look at it. Since arrow A and arrow B, and they are at the free end. Then this stuff is under the center. Arrow A and arrow B will be taking half of the because it's something like it's symmetrical or it's something like this one is this load is symmetrical at this point and then this point. You can just share it into two. They will carry half of it. Some carry half, because at the center of this and this. So we're just going to have something like our arrow A will now be equal to 5/2, which is let's say that's 2.5 newtons. Our arrow B will be equal to 5/2, so 2.5 newtons. But we not divide one by 2. Arrow B will be this over 2, arrow B will be this over because the loading is symmetrical. Then another thing is, let me solve the same question now. Let me solve the same question. Let's assume the pivot is at the free ends. Let's assume the pivot is at the free ends. The pivot is at the free ends. Then the loading, the beam is not symmetrical. This beam, no, the beam is not something like it's not uniform, not symmetrical. It's not uniform. Like one part is more heavier than the other. Now the other day we will discover that the weight of the beam was not somewhere here, which is it was now 40 cm to this right and 60 cm to this left. What will be the reaction like this? Will it be the same thing? No, because it's not at the center. It's not symmetrical about both sides. So we will just we have arrow A here, we have arrow A. This one is point A, and this one is point B. We have arrow B here, arrow B here. So how are we going to do this? The first thing. So let's just assume the weight of the beam is still just say, let's say the weight is still 5 newtons. Let's assume the weight is still 5 newtons. So how are we going to do the same thing, the same way? Everything is still very, very the same. The only thing that's wrong here is that beam is now 40 cm to A and the weight is now 40 cm to A and 60 cm to what? To B. So the only thing I'm going to do here is that the rules of moment still valid. Still what? Still valid. So what's the next thing now to do here? What is the next thing? The first thing say all upward forces will go to downward forces. That is arrow A is going up, arrow B is also what? Going up. But because of downward forces, which is what? 5 newtons. And now we say arrow A is not 5 but no, because 40 and 60 are not the same. It's not the midpoint of this and it. So you cannot share it, it's not possible. How are you going to look for arrow A and arrow B? Next thing, you will take moment about point A or point B or about the end of the beam. How do you take moment? That is another this thing. Look how to take moment. Alright, the moment is force times perpendicular distance. Force times what? Perpendicular distance. So this one now, over there is 40 cm, that is 0.4 meters. 60 cm, that is 0.6 meters. This one is 0.6 and 0.4. That's what I'm going to be using here. I'm going to use meters. This one is Newton. Newtons is a kilogram. Newtons is a mass times acceleration. It's kilogram meter per second square. So that's what I'm going to do now. Taking moment about A. Just taking moment about A. Take moment about A. Or you can also take moment about B when you like. You can do it. Then you're going to have the moment about A must be equal to what? The sum, not just the moment about A. The sum of the moments about A must be equal to 0. Sum of the moments about A must be equal to what? Must be equal to 0. That's another moment. And the clockwise moment, upward force equal to downward forces. The sum of all the moments about a particular point must be equal to 0. That's another one. Then I'm going to either use this one or anti-clockwise to clockwise moments. So let's check for at point A now. At this point, this load that is pointing towards this point will not give any moment. Take note of that. This one will give a moment of force times distance. So I'll give a moment of force times distance. I'm going to give those moments. Check it very well. Now, both of them are going to give moments. They are going to give moments, but what type of moment are they giving? One of them will give clockwise moments, another will give anti-clockwise moments. Now, which one will give clockwise moment? Now, you will take sign conversion. If clockwise moment is positive, anti-clockwise will be negative. So we have either clockwise or what? Anti-clockwise. Now, in this case now, I'm going to call clockwise, anti-clockwise positive, clockwise negative. That is how it is. You can either choose this one negative, you choose one positive. You are choosing clockwise to be positive, you choose anti-clockwise to be negative. You are choosing anti-clockwise to be negative, you choose clockwise to be what? Positive. That's how we rule here. It's not compulsory you must choose anti-clockwise as positive. No. If you are choosing one as positive, the other one should be negative. Both of them will be the same side. No. So I'm going to call anti-clockwise positive, clockwise negative. Then we'll sum up all the moments about this point and put it to 0. That is when you use this rule. Or you can just say, okay, let me know use that. So that means moments about A will not be equal to moments about A. Moments about A will not be equal to. So it must go to 0 for static equilibrium to be possible. So what are the moments about A? We have 5 times from there to here. That is, this one is check. This 5 now, assume this one was not here. How will this 5 rotate this beam about this point? The 5 will rotate the beam this way. So the 5 is going to rotate the beam this way. Abi? This way. And this way, is it clockwise or anti-clockwise? Check. Something like this. Is it clockwise or anti-clockwise? It's clockwise. See, it's going to rotate like this. About this point. So that's clockwise. We're going to have minus 5. This minus is telling us that it's clockwise. We said let clockwise be negative. Times, what's our potential here? 40 cm, that is 0.4 times 0.4. 40 cm is 40 cm. So meters is 40 over 100. That is 0.4 meters. That's what I'm trying to say. Then let's assume we now have this one here now. We also have this here. Then how will this arrow A? Because this one is arrow B. Let's see it first. Will it rotate this beam this way or rotate this beam this other way. Check. This arrow beam will rotate the beam this other way, this way. So that is anti-clockwise. You want to say plus arrow B. Then what's wrong between this and this place? This one from here to here is what? 6. That is 40 plus 60. That is 100. So that is 100 cm. Convert down to meters to be equal to 1 meter by dividing by 100 divided by 100. 1. So times 1 will equal to what? 0. So the next thing will be making arrow B formula. Arrow B times 1. That is arrow B. Then 0 guys, if you move minus 5 times 0.4 to the other side, will become plus 5 times 0.4. So arrow B is now arrow B will now be equal to this also 5 times 4 over 10. 5 times 4 over 10. 5 here, 5 here 1, 5 here 2. This divided by this. 4 divided by 2, that is 2 newtons. Arrow B is equal to 2 newtons. Now, what about arrow A? What about arrow A? We said arrow B plus arrow A is equal to 5 newtons. So arrow A can also be, move arrow B to the other side, 5 minus arrow B, which is 5 minus 2. That was 3 newtons. So therefore, for this other drawing now, our arrow A is equal to 3 newtons. Our arrow B is equal to 5 newtons. So these are you calculate reactions of beams. When you have this type of beam now, this one is just meter, we call it meter arrow, we say this one. But this type of beam now is called simply supported beam. You have roller at one end and the pin at the other end. It's called simply supported beam. Now let's look at question under this simply supported beam again, or meter arrow. Then also look at question that is what is it called? Cantilever beam. Right, let's look at this question. This under cantilever beam now. And the question is, write the question down. Now, they may not draw this out. They will not draw this question out. We just give you the question how to give now. You'll be able to sketch this out before you'll be able to solve. A non-uniform beam. A non-uniform beam of length 4.5 meters. A non-uniform beam of length 4.5 meters is hinged at one end in form of a wall. Is fixed at one end in form of a wall. A wall is not a hinge. A wall is a fixed end. Is fixed at one end in form of a wall. Okay, it's fixed at one end in form of a wall. And if the weight of the beam, okay, if the conception is hinge, no problem. If this is a hinge, then that means we have a wall here, we also have something like a hinge, a little hinge here. It's not actually that fixed. Because the question calls it a hinge in form of a wall. That means it's like a pin that is attached to a wall. And that means this place now is movable. That is what I'm trying to say. This is movable. If the weight of the beam is 170 newtons, which is 2.5 meters to the fixed edge, to the wall, is 2.5 meters to the wall. What vertical force at the free end that will support the beam to keep it from falling? Support the beam to keep it from falling. So what force will be here? What force are you to apply at this end that will support this beam and will keep this place from breaking or falling? So I can decide to remove this place and just put my reaction here is vertical reaction, which is arrow A. And this is the force I'm looking at. Just try to look at that force here. So the length of the beam is already from here to here, which is 4.5. The next thing, we are looking for the reaction at E. No, we are looking for the reaction at E. We are trying to look for this force that will keep this thing from I'll keep this beam from breaking or failing. So to look at this force now, what we're going to do, we'll take momentum at this point so that this force will be 0. If I take momentum at a particular point, the force pointing towards that point will be 0. So that will be, this will give us anti-clockwise, so that will give us clockwise. You can say anti-clockwise movement is equal to clockwise movement. That's what I'm going to use here now. I don't want to use some of all these movements at the point will be 0. No. I'm going to use anti-clockwise movement equal to clockwise movement here. So this anti-clockwise movement will be equal to clockwise movement. This one is anti-clockwise. So anything like this now. So this force that's coming like this now, that's going by this point. So the moment evaluation will be this force times this distance. That is anti-clockwise movement equal to clockwise movement. Anti-clockwise movement will be equal to clockwise movement. That's what I'm trying to say. What is anti-clockwise? This F times this. Because we move this way anti-clockwise. So that will be F times 4.5 will be equal to clockwise movement will be the one I will take, which is this. This one will take this one. So that will be the clockwise movement will be the one I will take this one. That will be 170 times 2.5. The next one we're going to do now will be, we have 4.5 F will be equal to 170 times 2.5. If I go start by 4.5, let's start by 4.5. And this will cancel this. The F, the first one equal to, this can be divided by this. I think we are going to produce 1 by 10, 25 divided by 45. Now something like 83 newtons, and the force I'll keep the beam from breaking or falling. That's what I need to have. Alright, so this force in 3.3 will keep this beam to be in the horizontal direction without either falling or swerving downward. So this force will keep it in that order. We'll keep the beam in that order. Now, let's look at another question. Alright, let's look at this last question for the day before we call it a day. And the question involves how to calculate the mass of a meter rule if you are something like pivoting in just one point or just one spot. You know, you can pivot a meter rule in how many spots you can. There's no much G about that. What you are saying is that, okay, let me call the question so that you see it. A meter rule of length 100 cm. A meter rule of length 100 cm. A meter rule of length 100 cm, that is the length of the meter rule, is pivoted at 60 cm mark. Is pivoted at 60 cm mark. Now, pivoted means it is supported at 60 cm mark. That you measure 60 cm from the end. It was supported at that point. It's pivoted at 16 cm mark, and it was found to be balanced. It was found to be balanced. Balanced in the sense that if you represent we pivot something of this nature, let's look at this now. Look at this. Let's see, it's not moving. Balance in the sense that the meter will not move again. That's what we are trying to say. This is what we mean by balance. Yeah, the meter will be balanced. It's found to be balanced when a mass of 100 grams, were placed at 12 cm mark. When a mass of 100 grams was placed at where? At 12 cm mark from the end. That's what I mean. It was placed at 12 cm mark from the end. Calculate the mass of the meter rule. Calculate the mass of the what? Of this meter rule. Calculate the mass of the meter rule. Now look at how to solve this question. Now what you just do, most of these questions may be asked without the drawing. So you have to sketch out the question. It says that you have to draw a meter rule. You have to draw a meter rule of length 100 cm. Then we pivot it either at this point by measuring 60 60 from here to here, or pi look at this way, I'm measuring 60 from here to here. So if I measure 60 now, the 60 cm I might be at this point, definitely not the center. So the pi is going to be there. In the sense that from here to here will be 60 cm. And what is 60 cm in meters? By dividing this by 100, we are going to have 0.6 meters. Divided by 100, we're going to have 0.12 meters. That's what we are going to have. Now, if you look at this, if this meter rule is something like a uniform meter rule, we have non-uniform rule. Non-uniform rule says that the weight of this rule will not be at the central or at the center of gravity. Yeah, let's go to the center of gravity. Now, center of gravity says that is the point at which the whole weight of the body will be acting on. So, the point at which this meter rule, now if it is not a uniform meter rule, then the weight of the body will not be acting at the center of the meter rule. But this one now is a uniform meter rule. Yeah, take a look, it is a uniform meter rule. If it is not uniform, we will tell you where the weight will be. Because we cannot get the weight for non-uniform meter rule just like that. So I will tell you, look at where the weight is. Like the first question we did, that non-uniform beam that was fixed to the wall. Can you see the weight was not at the midpoint of the beam? That's a typical example of non-uniform beam. Whether there's a uniform meter rule, we said that the weight will be at the center. Now, if you even check this with your eye, if I pivot this meter rule, if it's a balanced meter rule, if I pivot it at this point, say that the thing will not be balanced. It is going to fall to this side. It's going to fall to this side because of the weight. Now, what will I do? I'll try to hang something here. That's why this 100 gram came to balance the meter rule. And it balanced at 12 cm mark. So I'm going to measure 12 cm from this place. I'll measure 12 cm from here. So I'll have this point now. I'm now having a mass of 12 cm here hung in this place. So the mass was 100 grams. 100 grams. And to convert 100 grams to Newton, just divide. If you want to convert from grams to Newton, divide by 100. Like that, I'm going to have 1 Newton. That's what I'm going to do. If you want to convert to kilogram, divide by 1,000. If you want to just divide by 100. Then, when divided by 100, we are assuming that as relation due to gravity is 10 meters per second square. Please take note of that. It's very, very important. We are assuming for this acceleration due to gravity. Now, this is grams. This is acceleration due to gravity. Take note. This is acceleration due to this grams. Or this one is acceleration due to gravity. Take note of that. So, if acceleration due to gravity is not 10, don't go and divide by 100 to divide to Newton. No. That's what you do. Don't divide by 1,000 to divide to kilogram. Then you now multiply by 9 points or multiply by the value of acceleration due to gravity after you have converted it to kilogram. Think of that. Or I'm going to do it, let me just show you. So for conversion to kilogram by dividing by 1,000, that's 0.1 kg. So if G is giving us another number, use the G to multiply this, that will give you the weight in Newton. That's what I'm trying to say. Now, if I place this mass at this point, or is 12 cm from the free end, we actually like now discover that the meter rule will not be balanced. You know what? Will be balanced. So, what is the weight of the meter rule? The weight will be acting at a point which is the central or the center of the meter rule. If from here to here is 100, what will be the center? So what will be what? We measure from here to measure 50 out. Which is 50 cm. So the center will be at this point. So this will be the weight. Or let me just show you the weight of the meter rule. Remember, we want to go back from weight to mass. What do? We want to go back from weight to mass. What are you going to do? Divide the weight by acceleration due to gravity. We want to go back from mass to weight. Multiply the weight by acceleration due to gravity. That is all. So think of that is very, very important. So the weight will be acted this way. So this one we are looking for this weight. So automatically from here to here will now be 10 because from here is 60. From here is 50. So 60 minus 50, that is 10 cm. Then from here to here now automatically it will be 40. If I'm not, that's not a mistake. If from here to here is 60 cm, then will be 40. For that, everything will be what? Everything will be 100 cm. So everything is 100. So we have to put everything here. Everything is 100 cm. So 100 minus 60, that will give us 40. So if from here to here now, let's say from here to this place is 40 cm. 40 minus 12, what is that? That will give us 28 cm. Alright? That's all. So 2 plus 8, that is 30. 30 plus 10, that is 40. So let me redraw it again. It's very good because what I mean is I want to take my moment about this pivot. So I'm going to label it point A, point B, point C. So I want to take moment about that C now so that any other thing I don't need will go away. So to do that, I will just draw, let me just use this line to denote diameter rule. Then the next thing, let me just put the pivot here. Then the weight, we have a weight of 1 Newton here, which is 10 grams. Remember, we have to go back to Newton. What you want to do? The first of all, divide by 1000. Divide this by 1000. You use 10 to multiply by, I said, as you do want to be 10. If we are giving 9.81, you use how to multiply this to get this. That's what I'm trying to say. Take note of that. Then, we said from here to here is 28 cm. So, how we can convert 28 cm to meters? Then, we have the weight of the meter here, which is W. I will say from here to here is 10 cm. Don't know if you can get that. From here to here is 10 cm. Remember, 60 minus 50, 10. Then the next thing we're going to do now, we are going to take moments about this point C. Remember this point A, this point B, and this point C. Now let's take a moment about that point C to see what we're going to have now. So taking moment about point C, all anti-clockwise moments will be equal to this clockwise. This will be clockwise. Anything that will turn this beam this way will be clockwise. Then anything that will turn it this other way will be anti-clockwise. This is anti-clockwise. Why this is clockwise? Clockwise is saying that we move in the direction of our clock. That's not moving by clockwise. When it's moving in the direction of our clock, it's clockwise. When it's moving counterclockwise, or when it's moving something like in a counter form or opposite to the direction of our clock, call it counterclockwise or anti-clockwise. So it will be moving in this direction for anti-clockwise. So what are we going to do now? What are we going to do? 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 So we'll take one about this. So which of these two loadings will move this beam? Well, let's say anti-clockwise movement. Anti-clockwise movement will be equal to clockwise movement. The sum of all the clockwise movement will be equal to the sum of all the clockwise movement. Remember loss of moment now? Is sum of all anti-clockwise movement will be equal to sum of all clockwise movements. The sum of all the anti-clockwise movement will be equal to the sum of all the clockwise movements. Now let's check which one is anti-clockwise. Which one will turn this beam this way? Check. If you look at it. If you are looking at a particular moment of a force about the point, then you will assume the other forces are not present. You just take it as the other forces are not present. If this is the only force present, how will you rotate this beam? Or how will you rotate this meter rule about this particular point? Now let's assume this force is not present. How will this weight rotate this beam about this point? The weight, it will rotate this beam about this point, something like this. It will rotate the beam about this, like it's going to rotate it this way. Check. If you put a weight here, it's going to rotate it this way. Check. It's going to rotate it in this direction. So this is counter or anti-clockwise. So that will be W, this anti-clockwise moment, W times. What is the difference between this place and this place? Remember, moment is weight times distance or force times distance. So what is the difference between this and this? 10 cm. Now 10 cm is the same thing as 10 over 100, which is 0.1 meter. And the other one is 28 cm, this has 28 over 100, which is 0.28 meters. That's all. That's how to convert them. So we have this times this 0.1, which is 10 cm, times 0.1. Is there any other moment that will, is there any other force that will rotate this beam about this point? No other one again. Then it will be equal to, let's check for the clockwise movement now. This 1 Newton is going to rotate this beam this way. Check. If this 1 Newton is the only force here, it's going to rotate this beam along this, we just try and check it. We rotate this beam this way. We rotate this beam this way. Check. It's going to rotate it this way. This is clockwise. This is clockwise. So clockwise, some clockwise will not be. This we have only one. I think we have it 3. you just do this one plus the other one plus the other. Anything that will rotate the beam in this clockwise direction, add it together. That's the of that sum. Anything that will rotate the beam along counterclockwise and anti-clockwise direction, you add them together. That's the sum of the anti-clockwise beam. So that will just be 1 times what that will get here. Divide it down to meters and 0.28. So the next thing I'm going to do that will be making W the such that the formula W will now be equal to 1 times this. That is okay. We have 0.1 W will now be equal to 1 times this. We have 0.28. We have 0.28. Now dividing both sides by 0.1 so that W will be free. 0.28 over 0.1 or 0.1. This will cancel this. W will now be equal to, divide this by this, we will have 2.8 newtons. That's what we have. 2.8 newtons. That is the weight. Now, to get the mass now, remember G. To get the mass of the meter root, we are getting the weight of the meter root. If you have gotten weight, to get mass is very simple. Remember we are using G. Recall that G was, I said G gravity was what, 10 meters per second square. What you just do is just to get the mass now, just use G to multiply the U. Or because the U is set as mg. I don't think I have forgotten. So to just get mass now, divide the A by G. That will give you the mass. That is the mass will now be this is weight is equal to mg. So mass is equal to weight over G. Please, sorry about that. Mass is equal to weight over G. That's what. Mass is equal to W over G, which is W is 2.8. That is the weight of the meter divided by G, which is that is 0.28 grams. Okay, it should not be in grams because we are working with Newton. It should be in kilogram. So this is in kilogram because we have meter, kilogram, meter, seconds. You can still remember that. Newton is as unit for force, which is kilogram meter per second squared. So we should be in kilogram. This one is in kilogram. So to move the mass to grams now, multiply that by 1,000. That's what we're going to do. So the mass will become 1,000 times 0.28. That is 280 grams. That is the mass of the meter root. This is the mass of the meter root in grams. This is the mass of the meter root in kilogram. This is the weight of the meter root in Newton. So the option is going to either come this way as the correct option, or this, any of them will come aboard as the correct answer to this particular problem, which is to get the mass of this meter root. But the mass will not be in Newton because mass is in kilogram, not in Newton. I say, what is the weight of the meter root? The weight will be 2.8 Newton. I say, what is the mass of the meter root? So that is 0.28 kilogram or 280 grams. Any of the two will be very, very correct. So see if you are correct, just check. 1 times, just do this way. Just do. Check if this movement, if this one is, we are not saying that this will be 2.8 Newton. That's what I'm trying to say. I say this one will be equal to 2.8 Newton. Just check. 2.8 times 10, that is 0.1 meters. 2.8 times 10, that is 0.1. Will it be equal to 1 times 0.2? We check. 1 times 0.28. Now that is 0.28 is equal to 1 times 0.28. You see? Anti-clockwise is equal to clockwise movement. So that is the mass. So if you do it this way, the thing is, since anti-clockwise is equal to clockwise movement, since the anti-clockwise is equal to what will happen? What happens is that the thing will be in static equilibrium. Be in equilibrium, to be balanced. So that would be the mass of the meter root for this beam to be balanced. So take note of that. This is the weight, this is the mass in kilogram, this is the mass in grams. So please don't forget. Thank you all. This is all where we stop for this movement of the force. We know in our next class we're going to do friction, do the relation of forces, and so on. So we have already done parallel of forces. We've done parallel of forces. Try and look at parallel of forces, which we have already in our channel. Try and look at it. Parallel of forces and the rest. So we are going to do the relation of forces, Lami's theorems, law of triangle of force, and the rest. Thank you. See you guys in our next class. God bless you. part of our videos. Thank you. God bless you. Thank you.